Hello students, in this video I am going to explain Unit 4 Tables Obst Binary Search Tree. Let us see the contents of this unit. It contains symbol table, Obst, Huffman algorithm or Huffman coding, heap data structure, min heap, max heap, heap sort, application of heap and hashing. Obst, heap, hashing, all these are the representation of the symbol table. We already discussed in a classroom about the symbol table, Huffman coding, heap data structures. All of you solved the problems of the heap data structures as well as Huffman coding. Let us see the previous year questions which are asked on this particular unit. In May-June 2017, they asked the question on heap sort and show the sorting stepwise. We solved this example in classroom. Then show the stepwise construction of max heap for the data. What is symbol table? Give the symbol table. Apply the max heap sorting technique to sort. Then again, there is a question on Huffman coding. We solved this example in the classrooms. Okay. Now in this particular video, I am going to explain you the optimal binary search tree which is not covered in a classroom. Now what is the optimal binary search tree? Before going for the optimal, all of you know the binary search tree. In a binary search tree, left subpart or left subtree is smaller than the parent, whereas the right subtree is greater than the parent node. There may be a different BST for the collection of the same elements on the selection of the root node. So there may be a different number of comparison for searching a key element. Binary search tree is very useful for searching an element in a log n time. So for the same elements you can create different binary search tree by taking the root different. So there are the different comparisons for searching a key element. If we know the probabilities of searching each key elements of the tree, then the expected cost of accessing tree can be easily found. Obst is a special kind of binary search tree which has minimum expected cost of accessing the tree or minimum number of comparison for accessing the tree. We directly take the example for understanding the Obst. Assume that there is a binary search tree with 3 nodes, that is do, if and stop. So different binary search tree can be constructed as do as a parent node, if as a parent node, stop as a parent node or root node. Different possibilities are there for constructing a binary search tree. The probability of searching the element is or accessing the element is also given in advance, that is 0.4 for do, 0.5 for if and 0.1 for the stop symbol. Find the expected access time in each case and also find the optimal binary search tree. So how to solve it? First we assume that the stop, that is the third word, is a root node. Okay, so you know the property of binary search tree. The left is always smaller than the parent, right is greater than the parent. So you are arranging it in this fashion: I is less than S and D is less than I. So all are coming in the left side. Now you know the stop is at level 0, if is at level 1 and do is at level 2. Then you know the probability of accessing the stop is 0.1 and what is the depth of the stop? It is 0 because it is at level 0. Probability of accessing if is 0.5 and its depth is 1. The probability of do is 0.4 and D3, that is the depth of this is 2. Now we'll solve this by using expected access time as summation of I1 to n probabilities into the depth plus 1. So when you are calculating the number of comparisons, you have to take the depth plus 1 because you are comparing it, and then so comparison is made at every depth, so it is plus 1. Then start with the first, that is P3. P3 multiplied by its depth plus 1. So P3 into D3 plus 1 plus P2 into D2 plus 1 plus P1 into D1 plus 1. So it's a summation of the probabilities multiplied by the depth plus 1. So after solving this, we'll get the answer as 2.3. This is your first binary search tree with stop as a root node. Now we can think for another binary search tree with if as a root node. So if you choose the second node as a second symbol or second word as a root node, the do is coming on the left side whereas stop is coming on the right side. If you observe this, this is a biased binary search tree. Now we will see the probability. This is already given in the problem. You just mention the depth. So depth is here 0 because it is at the level 0. This is at level 1. So its depth is 1. Its depth is also 1. Your formula of calculating the expected access time is same. It remains same. You have to just put up the values, appropriate values in the probability and the depth, and you will get the answer as 1.5. If you observe these two binary search tree, the expected access time is here 2.3 and here it is 1.5. It's very less as compared to the previous binary search tree. So this is your second binary search tree. Now we'll go ahead with the next combination where the do, that is the first key word, is the root node, and if you are choosing this as a root, obviously if and stop it goes to the right side. Now again use the same probabilities which are given in the problem. You just mention the depth is changing in every binary search tree. So here depth is 0, here depth is 1, and here depth is 2. So you put up the value in the formula and you will come with the value as 1.7 as a expected access time for this BST, okay, for this given binary search tree. Now we'll go for another combination where the stop is a root node, then we go for do, and then we go for the if. So this is another combination. So again you have to calculate the expected access time for the given tree using the same formula, and you come up with the value as 2.4. Now next is you will go for one more combination of the tree, that is do, then you go for the stop, and then you go for the if. So again here the depth is changed accordingly, and you have to put up the values in the formula and you come up with the 2.1. So if you, here we have seen the different binary search tree for the same input symbol, or for the same input we are having the 5 binary search tree. Out of this, only one binary search tree which is having a minimum expected access time, that is the binary search tree B, which cost is 1.5. So this is the optimal binary search tree with the cost of 1.5. Now there are two types of the search possible on a tree, binary search tree. Either a successful search, means the word is found, and unsuccessful search where the word is not found. Let us take an example, the same example, do, if, and stop. These are the three keywords or the symbols. Now P1, P2 and P3, these are, what is this? What is this? This is nothing but the probability of occurrence. That do is occur with the probability P1, or if is found with the probability P2, stop is found with the probability P3. So this is the probability of success. Now what are the probabilities of unsuccessful search? You are searching for a word and which is less than do, a word before do. Okay, so that probability might be a Q0. Then you are searching for a word which is not do and which is not if, but it is in between do and if. So a word is between do and if. So you are trying to search. It is a unsuccessful search. Okay. Then you are searching for a word which is between if and stop. So it is a word between if and stop. And the word that you are searching which is after stop. So these are the probabilities of unsuccessful search or a failure. Okay, so there are two types of probability. One is the probability of success and the probability of failure. And the symbols are given. To consider this problem, list the binary search tree with three nodes, do, if and stop, with the probability of success is 0.4, 0.2 and 0.1. And the probability of unsuccessful search is Q0, Q1, Q2 and Q3. That is 0.1, 0.1, 0.05 and 0.05. So Q0 means before the do, Q1 is between do and if, and Q2 is between if and stop, and Q3 is after stop. So you are searching for a word which is not present in a binary search tree, so that is the unsuccessful search or a failure. So find the expected access time in each case and also find the optimal best. So we'll consider the same binary search tree that we discussed previously. So first is you start with the stop, then your second word, and finally is a do. This is one combination of the nodes. Now in the given binary search tree, you have to add the failure nodes. Okay, in the form of the square. This square is indicating the failure nodes. So before do is Q0, do and if is Q1, then if and stop is Q2, and after stop is Q3. So you have to add the appropriate failure nodes in a binary search tree and also mention its probabilities. So P3, P2 and P1. So these are the probabilities given in the problem. You also know the probability of the failures. Okay. So accordingly, now change the expected access time or the number of comparisons as the probability summation of the probability of success into depth plus 1 plus summation of the probabilities of failure into the depth of the tree. So here you don't go for the plus 1, where here you have to go for plus 1. So this is the only change while doing the calculations. So how you can solve it? It's start with the first, that is P3 into D3 plus 1. Okay, because it's the probability of success. So the next is P2 into D2 plus 1. Then P1 into D1 plus 1. Then you have to go for Q0. Q0 into DF. It's the depth of failure. So what is the depth of Q0? It's 1, 2, 3. So it is at level 3. So its depth of failure is 3. Don't go for plus 1. Then Q1 is, the probability of Q1 is 0.1 into its depth. Depth is 3. What is the depth of Q2? Its depth is 2. Q3 depth is 1. So accordingly, you have to put up the values in the formula and you come up with the value that is 2.45. This is your first binary search tree. In a similar manner, you can go for one more binary search tree with if as a root node and do and stop is the left and right child. So you have the P2, P1 and P3. Along with that, you have to add now the failure nodes, that is Q0, Q1, Q2 and Q3. So you have to add this failure nodes. Now this is as a child. Okay, so all are at the same level, that is 2. Okay, so here 2 is multiplied for the probability of failure and the depth plus 1 is multiplied with the probability of success, and you come up with the value as 1.8. Now with this similar guideline, you have to calculate for the other trees and find out the optimal binary search tree which has the minimum access time. Thank you.